probability. There's only, again, one set of homework and just one quiz over probability. And then we're going to move on. We won't get through all of this today, but we'll finish it up after Mardi Gras, and then we'll go over chapter 6. So 4, 5, and 6 are going to be on our test, which is March 20th, I think. It's on a Wednesday. And I've got the study guide already posted, but we've only gone through one chapter out of the 3, so I don't really need to worry about that just yet. But it's up there. All right, so probability rules, we're just going to go through a few of them because we're going to need them basically for chapter 6 when we calculate probabilities for discrete random variables. So we've got a few definitions starting off. Probability is a measure of the likelihood of a random phenomenon or behavior occurring. So what it's going to do is it talks about in the long term, what proportion are you going to get a certain outcome with? And then we can use that to describe what's going to happen in the short term. So it's going to be a certain outcome that's going to be what you would expect to happen. So probability, we're looking more long term, what happens if you do it a large enough number of times. So if you are looking at rolling a die and you are looking, what's the probability that I get a 2? Well, the probability would be 1 out of 6, but that doesn't mean if you roll a die 6 times, you're guaranteed to get a 2 one time out of those 6 times, because short term isn't really all that close to what the actual probability is going to be. But if you roll a die, say, long term, if you do it maybe like 6,000 times, you would expect the number of times that you get a 2 to be a lot closer to 1,000. So a lot closer to being that actual 1 out of 6 times. So the longer you do these things, the more your actual outcome that you actually see, the observed value, the number of times you actually observe it is going to get a lot closer to your actual probability if you do it a large enough number of times. Not so much if you do it just a short number of times. So, yeah.
Do they use probability with like the lottery system and like picking winners?
You can calculate the probability, like if you get like a ticket with certain numbers, you can calculate the probability that you'll win. It's really small. So I don't even know what numbers we use for a lottery, but we could if you wanted to. I just have to do some research and figure out what numbers they use, but we can calculate the probability that you would win. We'll do a little more with that with expected value, I think, in chapter 6. I think we've got a problem that's similar to the lottery in that one,
Okay.
where we go through and calculate that.
Thank you.
Yeah. I'll make a note and we'll go through and talk about actual like lottery and figure out the probability that you'll win. It's not high.
Gotcha. Appreciate it.
And there's no good method because otherwise all the mathematicians would be winning, but we're not. So my uncle keeps asking me to pick his numbers for him because I'm good at math, and I'm like, that's not how it works. Anyway, so we're looking at short-term results or outcomes, but we're basing it off of what's going to happen long-term, not necessarily short-term, because long-term is going to be more accurate if we look at doing these experiments a large enough number of times. Okay. So if you look at long-term, the proportion that you expect to see the outcome happen, that's going to be what our probability is of that outcome. And there's 2 different ways we can calculate probabilities, and we'll get to those later. Right? I have it in the wrong order. All right, we've got the law of large numbers. So that just says if you do this experiment a large enough number of times, the proportion that you see the outcome happen is going to get closer and closer to the probability of the outcome. So again, if you roll a die, if you do 6 times, you're probably not going to get exactly 1, 2. But if you do it 6,000 times, you're probably going to get pretty close to 1,000 twos. Pretty close. And then if you do it like 6 million times, then you probably really should get pretty close to about 1 million of those observations are 2s. So we have to do it a large number of times, but large is kind of ambiguous, but they just say large. Kind of just depends on the experiment, how many times you need to do it in order for it to be large, which we'll get to in chapter 8, I think. All right, so an experiment is a process that is going to be repeated in which your results are uncertain. So, like I said, things like rolling a die, drawing a card, flipping a coin, those can all be experiments. And then we've got our sample space, they call that capital S. And that's just going to be a collection of all the different possible outcomes. So if you're flipping a coin, your sample space would be heads and tails. If you're rolling a die, your sample space is 1, 2, 3, 4, 5, 6. If you're drawing a card, your sample space is going to be all of the 52 possible cards in the deck. And then an event is a collection of outcomes from your sample space. You can have one outcome, or you can have more than one outcome. So if you're rolling a die, you can have what's the probability that I roll a 2, or you can say what's the probability that I roll an even number, in which case that would be a 2, 4, or a 6. So with an event, it can be one outcome, or it can just be a group of outcomes. All right, if there's only one outcome in the event, we call those simple events, and they call those a lowercase e for a simple event, and they put an I there just to denote which one it is. That's just a little bit of notation. The simple event would be a lowercase e. Really, we just use that for a definition later on in the next one, but we usually don't use these lowercase e's, except for defining formulas and such. But if you have just any event in general, they usually call it a capital E for event. So now we've got this example. We've got this probability experiment where we've got 2 children. And we're going to look at their genders. They don't really say that that's what we're looking at, but they're expecting us to know that we're looking at the gender of having 2 children. So if we're going to identify all of the different possible outcomes of the probability experiment, we've got, so part A, if you list the outcomes, you can either have, and I'm going to abbreviate with these ones instead of writing it all out, but your outcomes, you can either have 2 boys, you can have a boy and then a girl, you can have a girl and then a boy, or you can have 2 girls. Bless you. Okay. Notice that we treat these 2 differently if the boy is older or if the girl is older, so altogether we have 4 different possible outcomes for this one. All right, so we've got 4 outcomes. Each of these would be a simple event. 1 simple event, 2, 3, 4 simple events. Okay, so part B, when they ask you to list out the sample space, sample space is just listing out all of the different possible outcomes you could have. So part B is going to be basically just the same thing as part A, but usually when they list the sample space, they just put curly brackets around it. So for part B, it's going to look exactly like A, but we'll say curly brackets, because when you use curly brackets, that's the set of all of these outcomes that you have here. So we'll have BB and BG and GB and GG. And then close your curly brackets. So that's our sample space. They just put curly brackets around it when they're talking about a set of possible outcomes. But really A and B are